Okay, let's take a look at a couple more examples of working with binomial distribution questions and approximating them with a normal distribution. Remember, the key ideas that we need to work with here is that the binomial distribution can be approximated using the normal curve that has mean n times p of n trials, constant success probability p, variance sigma squared equals mpq, or mp times 1 minus p. Okay, and then we, since we're talking about binomial distributions, we have a discrete case being approximated with a continuous probability, so we need a continuity correction there of usually a half unit to account for potential rounding. So in this example we're going to start out with today, let's take a look at flipping a coin 400 times. So let's start out a new example here. A coin is tossed 400 times. A coin is tossed 400 times. All right, let's approximate the probability of obtaining. Approximate the probability of obtaining. We're going to look at two parts here. A, fewer than 175 or more than 223 heads. $223 heads. So we're going to look for that. And then part B, exactly 205 heads. Exactly 205 heads. Okay. All right, let's take a look at what we have here. A coin is tossed 400 times. So if X is going to count the number of heads that we get, X is going to count the number of heads that we get. This is binomial. We have n equals 400 trials. Success probability here going to be 1/2, assuming we have 1/2 fair coin. So n times p then, n times p, 400 times a half, that's 200. 400 times a half, that's 200. And npq, or mp times 1 minus p, that's going to be 200 times a half, or 400 times 1/2 times a half. So there we go, and that is 100. Nice. Everything looks good. So let's go ahead and take a look at this. We're going to approximate X with a normal distribution. We'll say X is approximately normal. X is approximately normal with a mean mu of 200 and a variance sigma squared of 100. If the variance is 100, that means the standard deviation is equal to 10, right? That would be the standard, means the standard deviation is equal to 10. So let's take a look at part A. Let's take a look at part A. Fewer than 175 or more than 223. Okay, so let me see here. So for part A, fewer than 175 or more than 223 heads. We have a mean of 200 here, right? So if I think about drawing a normal curve centered with a mean at 200 there, maybe I'll make that a dashed line real quick just so. We're looking for fewer than 175. So 175 is over here to the left, or more than 223. More than 223. So we want this area to the left or this area to the right. Huh? Yeah, that looks good. Okay. Now, thinking about, gotta be careful here with your continuity corrections. We're going to be looking at, if we're going to go to the left, if I got 100, I'd want to count like 175.4, right? Because that would round down to 175 heads. So I want to make sure that we are going to be less than 175.5, because that would round down, right? So I should include up to 175.5 on the lower bound. On the flip side of that, though, the 223, I don't want to look at 223.5. I don't want to look at 222.5, because that would round up. That would round up. The 222.5, that would round up to 223. So I want to make sure I am including that in my my probability computation, right? So let's see here. We're looking for the following, the probability. So x, we gotta be, careful. We should be really careful here. Fewer than 175. Fewer than 175. I actually don't want to include 175, right? So let's write this out exactly. These are all strict inequalities. This is not including 175, and it is not including 223. These should be non-inclusive, so I don't want to include 223, and I don't want to include 175. So we need to adjust what we have here. Let's get rid of that. Fewer than 175. Fewer than. So not including 175. Not including 175, right? Notice in our definition that we had, what we had here, this is less than or equal to. Less than or equal to. Now, in a typical continuous problem, that is irrelevant, but in a discrete case, it is relevant. So I'm going to go ahead and translate this to equals. If I am, let's see here, fewer than, this is wrong. This is wrong too. Fewer than 175 or more than 223. Fewer than 175. What I had written, that compounding inequality, was the area in between. I want this or more than 223. There we go. This is what we want. This is the desired probability. There we go. Now, what do we have here? So this less than 175 would be less than or equal to 174. It would be less than or equal to 174. And greater than 223 would be greater than or equal to 224. Okay. So we want to include 174 and we want to include 224. Then I want to add my extra half units here, in the sense that I want 174.5, because that would round down to 174. So this is, according to the normal distribution, this is approximately equal to the probability that z is less than or equal to 174.5 minus 200 minus our mean over our standard deviation of 10, plus the probability that z is greater than or equal to, now the 224, since I'm going greater than, I want to include a half unit to the left here. So that's going to be greater than or equal to 223.5, right? Because you think about this, 223.5 would round up to 224, so I should include that. Minus our mean of 200 divided by 10. Those are the probabilities that we are looking to compute. Okay, so let's see what we have here. 174.5 minus 200 is negative 25.5, and divided by 10 is negative 2.55. So z less than or equal to negative 2.55. We can look that up in the table. Plus the probability that z is greater than or equal to 223.5 minus 200, and then we divide by 10 there, 2.35. Okay. Good. So we can go ahead and look this up in a table, and then the probability that z is greater than 2.35, we can look at the complement probability, so we can use the table there. So the probability that z is greater than or equal to 2.35, we can look at 1 minus the probability that z is less than or equal to 2.35. And so that would be 1 minus. So let's go ahead and take a look at the table for 2.35. Where's my table here? 2.3, 2.3, 2.30, 1, 2, 3, 4, 5. 0.9906, 0.9906, 9906, 1 minus 0.9906 is 0.0094. So this piece is 0.0094. And then what is less than negative 2? What is less than negative 2.55? So negative 2, negative 2.5, 0, 1, 2, 3, 4, 5 is 0.0054. 0.0054. All right, so we add these together, 0.0054, 0.0094, 0.0148, 0.0148. There we go. That is the approximate probability of getting fewer than 175 heads or more than 223 heads when you are flipping it 200 times. 0.0148. Okay, sorry. Got a little bit scattered at the start there, so certainly maybe expect some questions or clarifications. Post those in the discussion thread below. I'm going to move on to part B, looking for exactly 205 heads. Part B, we want exactly 205 heads. Okay, so, well, exactly 205 heads. This is kind of an interesting question because in a continuous sense, we would say the probability of getting exactly 205 is 0. But this is a discrete probability question, so there should be a positive probability here. So if we want exactly 205 heads, we have a mean of 200 here. Right? We have a mean of 200 in our distribution and a standard deviation of 10. So exactly 205 heads, 205 would be right here. This is what we want, okay? So what would round to 205? Well, that would include up to 205.5 and then down to 204.5. All of those would round to 205. So we actually do have a range that we can compute with our continuous probabilities here, right? The probability that x is exactly 205 is approximately the probability that a standard normal random variable z is between 205.5 minus the mean over the standard deviation and 204.5 minus the mean over the standard deviation, right? We have that range that we're allowed to get for rounding. So what is 204.5 minus 200? That's 4.5 divided by 10. So this is the probability 0.45 on the left for z. 205.5 minus 200 is 5.5 divided by 10 is 0.55. And so we're looking at finding the those values in the standard normal table. All right. Exactly 205. If we had 205.1, that would round to 205, right? So we have a continuous range that we can look at here. So let's go ahead and look at these in the table. What do we need to do to figure this one out? We're going to need to look at the probability that z is less than 0.55. We'll subtract the probability we don't want. That's everything below 0.45. Let's go look up these two values in the table, 0.55 and 0.45. 0.55 is right there, 0.7088. And 0.45 is right above it, 0.6736. So 0.7088 minus 0.6736, 0.0352. 0352. What a 3% chance of getting exactly 205 heads here. Exactly 205 heads. Okay. This is kind of interesting just in terms of looking at the numbers. You think about all the possibilities that are allowed in scenario A. Fewer than 175 or more than 223. Right? There is a wide range of acceptable outcomes that would satisfy that if you flip a coin 400 times. It's a very specific range when you say exactly 205, yet this has a greater chance of occurring. It kind of just sort of goes to show that the more you are flipping your coin, as n gets larger and larger, the more narrow our distribution gets, and we should expect something much closer to the mean on average. So 205 being very close to the mean of 200 is more likely than these 175 and 223. Those are extreme cases. And anything beyond that is even more extreme. So that's what we're looking at for these two parts right there, okay? Good. All right. I want to do one last example then to kind of close this one up. I like this example because I sort of think of it as a neat little application question that's maybe something we can relate to. Got a nice little business application here. A common business practice is to oversell tickets. A common business practice is to oversell tickets. And this is usually the thing I'm most familiar with are traveling. So plane tickets, maybe bus tickets and things like that, because not everyone is necessarily guaranteed to show up. And so they will oversell them. I'm not sure if they do this for events or concerts or things like that, but you've probably seen this at an airline if you've ever flown before. So let's suppose that the percentage of no-shows, that the percentage of no-shows, these are people who buy a ticket but don't show up, at flight time is 2%. At flight time is 2%. I'm not sure how accurate this number is at all in terms of like reality, but it's relatively small. And I think it's reasonable to say that, given how many flights you think Delta Airlines does over the course of a year, that they've probably got a lot of past data. So you can come up with a reasonable estimate of the percentage of no-shows. So let's just take a look at how this might work. A question you might be asking is, what is an acceptable amount to oversell your tickets, right? So let's say that for a particular flight that has 219 seats, for a particular flight with 219 seats, a total of 225 tickets were sold. A total of 225 tickets were sold. Okay. What is the probability that the airline overbooked the flight? What is the probability that the airline overbooked the flight? What is the probability the airline overbooked the flight? Well, that would be basically 219 or more people would show up. You'd have 219 or more people show up. Okay. So I'm curious. The percentage of no-shows at flight time is 2%. All right. Just as an FYI, if you do, and you look at 225 at over 219, that's 6 oversold. They've oversold it by 6. Okay. That is actually a 2.7% extra. Six more tickets. That is 2.7% over the 219. That's pretty close to the expected number of no-shows, which is 2%. Right? That's pretty close. So, what is the probability the airline is overbooked? My gut reaction, since it's close to the 2%, is my gut reaction is that it would be low. Let's see if that gut reaction is correct here. Okay, so how do we analyze this? If some of the verbiage is maybe a little confusing, it is overbooked. The flight is overbooked when there are not enough no-shows. When there's not enough no-shows. If enough people don't show up, then the flight is fine. So the sort of success idea here, what we want to be counting, is the number of no-shows. The number of no-shows. What is the mean number of no-shows here? There are 225 tickets sold. There are 225 tickets sold. Not 219, there's 225 tickets sold. And so the expected number of no-shows then would be 2% of the number of tickets sold. So 225 times 0.02 is 4.5. And the standard deviation then of the number of no-shows is the square root of 4.5 times your failure probability, which is 0.98. That's the square root of MPQ. That is 4.41. You take the square root of 4.41. It is exactly 2.10. Exactly 2.10. Okay. So again, to write this out and how we're counting this, for the flight to be overbooked, for the flight to be considered overbooked, the number of no-shows, is at most what? X is counting the number of no-shows. If the flight is overbooked, what's the most number of people we can have not show up and still not have enough seats? That would be 5. That would be 5. If we sold 225 tickets and there are 5 no-shows, that means there are 220 people trying to get into 219 seats and it is overbooked. If 6 people don't show up, then the flight is full at 219 and we're good to go. So the number of no-shows is at most 5. So we're looking at the probability then that X is less than 5. We can approximate this then with our normal curve. Continuity correction here would be 5.5, an extra half unit. Subtracting the mean divided by the standard deviation. So this is the probability that Z is less than 1 divided by 2.10 is 0.476. So in the table then, we're going to have to look up 0.48 or take a value that's roughly somewhere between 0.47 and 0.48. Let's go ahead and take a look at what we have in the normal table here at 0.476. 0.47 is here. 0.48 is here. So something like 0.6808. We're actually closer to 0.6844. We're closer to 0.6844. So that would be the table entry I would take is 0.6844. If you wanted to, this is almost in the middle here. So you could take an average if you want of these two values. You could do halfway between 6808 and 0.6844. Either one should be considered acceptable. I would, in fact, just take this value out of the table. Okay? Good. So, 68%. That's a high probability. That's a high probability. It is more likely to be overbooked than not overbooked. 68% chance. That is worse than a coin flip. That is, I would say, if I was an airline operations manager, that is oversold too much. Oversold by too much, in my opinion.